Hi, I'm Dr. Jim McGinley from Vector Psychometric Group. In this video, I'm going to talk about hierarchical linear modeling, or HLM, also known as multi-level random effects or mixed effects modeling. Together, we'll dive into some basic HLM concepts and run through a quick demo of the models in action using version 8.2 of our HLM software. Broadly, we can think about HLM as a framework for handling nested data structures. For example, consider we have a population from which we sample some higher level macro groups. These could be things like schools, hospitals, or companies. Then, within each of these macro groups, we assess micro units such as students, patients, or workers. In HLM or multi-level lingo, you will frequently hear people say that the level 1 micro units are nested within the level 2 macro units. Nested data structures arise everywhere in life. A classic example is in education, where students at level 1 are nested within teachers at level 2. We can also find nested data appearing in other disciplines, including the social sciences, medicine, public health, and business. A natural question that arises when first hearing about HLM is, why do I need this when I'm already comfortable with standard approaches like linear regression, ANOVA, and t-test? The simple answer is dependence, which these common techniques do not address. Dependence occurs because micro units within the same macro group are more similar to each other compared to micro units from other macro groups. Put another way, micro units within the same macro group are correlated. Now this is an econ class, so I'm going to get away from the micro-macro terms a bit. And we can easily show dependence with an example. Imagine there are two different families, each consisting of 3 boys. Call one family the Hansons and the second family the Mannings. If we are looking at musical ability, Taylor and Zach Hanson will be more similar to each other compared to, say, Zach Hanson and Peyton Manning. Likewise, if we look at the ability to read NFL defenses, Peyton and Eli Manning's skill levels will be more alike than Peyton Manning and Isaac Hanson's skill levels. And that, in a nutshell, is dependence. Ignoring dependence can cause several problems. Clearly, it violates the assumption of independence associated with standard modeling approaches like linear regression, ANOVA, and t-test. And not accounting for the within cluster or group correlation can have a real impact on your results. For example, the standard errors are often too small, which in turn leads to incorrect p-values. From a substantive view, ignoring dependence also impacts one's ability to draw valid and reliable inferences at both the micro and macro levels. This is an important drawback because, in practice, predictor effects can differ across contexts. HLM offers several unique benefits for nested or clustered data. First, hierarchical linear models explicitly account for dependence by modeling the clustering in a way that permits the examination of both level 1 and level 2 effects. Second, HLM is conceptually easy to understand and execute in practice. It is often the case that the HLM framework maps closely onto a person's research questions because HLM naturally disaggregates within versus between cluster contexts, which are commonly of interest in applied research. Third, HLM generalizes well. For instance, by including random effects, model results generalize to the population of level 2 macro units instead of only those sampled. Lastly, although outside the scope of the current video, the HLM framework is flexible and provides a basis for a variety of advanced modeling approaches. One of the potential downsides of the widespread nature of nested designs is terminology. Often across or even within fields, hierarchical linear models may be called by different names including
multi-level models, linear mixed effects models, random effects models, random coefficient models, random parameter models, and nested data models.
Likewise, the nested data structures may be called
clustered data, hierarchical data, group data, dependent data, or multi-level data.
Be aware these are all the same thing. I'm highlighting this because nomenclature is often a big point of confusion, so again, be aware of this when you're embarking on your HLM journey. Next, I'm going to introduce the random effects ANOVA model. An essential part of understanding and fitting two-level hierarchical linear models is digging into two basic equations. The level 1 equation references the lowest level of the model. This is all about the micro units, which are often individuals like students, patients, or employees. The level 2 equation addresses the highest level of the model. This is about the macro units. These are often things like classes, hospitals, or companies. To help break down these equations, I'm going to build on a hypothetical example where we have employees at level 1 nested within teams at level 2. In our simple example, we are looking at employees' ratings of job satisfaction on a 0,
low,
to 10,
Hi.
response scale. In this illustration, we have 5 teams, and every team has 5 employees, so there are a total of 25 employees. A really quick note on notation: the text says there are J equals 5 teams and I equals 5 employees. This is because in the HLM equations, J is used in reference to teams, the level 2 units, and I is used in reference to employees, the level 1 units. This will become clear as we work through our example, so let's start by taking a look at the level 1 equation. The level 1 or within team equation shows that the observed job satisfaction score for employee I in team J, denoted as YIJ, equals the average job satisfaction score for team J, denoted as beta 0J, plus the residual for employee I within team J, denoted as RIJ. There are 2 other things to take note of. First, beta 0J, which represents the team-specific means, is also known as the random intercept. You will hear this phrase frequently when reading about HLM or multi-level modeling. Second, the residuals are just the difference between the observed employee scores, aka YIJ, and the team-specific means, aka beta 0J. These are assumed to be normally distributed with a mean of 0 and variance of sigma squared. It is important to know that sigma squared may be referenced in various ways, such as the level 1 variance, within team variance, or residual variance, depending on what you're reading. Now, let's take a stab at visualizing what this level 1 equation means. So here we are plotting the observed job satisfaction scores on the vertical y-axis against employees on the horizontal x-axis for just team 1. Recognizing the observed scores, YIJ, is simple. They're just the blue dots. But notice the notation next to these dots. The first subscript, I, denotes which employee it is, and the second subscript, J, is a constant 1 because we are looking at team 1 here. At this point, you're probably dying to know more about the team-specific job satisfaction mean, or beta 0J. Voila! We add a horizontal line that shows the average job satisfaction score for team 1. Team 1's average score is about 7. Last, but certainly not least, we can visualize residuals by examining the differences between each employee's observed score and the team-specific average. Smaller deviations around the team mean result in a smaller sigma squared, or level 1 variance. This indicates less within-team variability around the group mean. Bigger deviations around the team mean result in a larger sigma squared, or level 1 variance, indicating more within-team variability. Again,
Small, big. Small,
big.
Small.
big,
Moving on to the level 2 between team equation, we can see that beta 0J, the random intercept, which represents team J's mean job satisfaction, equals the overall mean job satisfaction in the population, denoted as gamma 00, plus the residual for team J, labeled as U0J. This level 2 residual represents the difference between team J's mean job satisfaction and the overall mean. You can also think about this term as the unique effect of team J on job satisfaction. Either way, we assume that U0J is normally distributed with a mean of 0 and variance of tau 00. This variance may also be described as the level 2 variance, between group variance, or random intercept variance depending on the research setting. Next, let's get visual with the level 2 equation. Previously, in level 1, I showed how we can think about team 1's mean job satisfaction. Here we can extend that process by plotting the team means for each of the other 4 teams. Note that across teams, mean satisfaction ranges from about 5.4 to 8.1, and no teams have the same level. However, we can calculate an average of the respective group means, and this gives us an overall mean job satisfaction, labeled as gamma 00 in the level 2 equation. Further, by looking at differences between the team means and the overall mean, we get U0J, also known as the level 2 residuals or unique team effects. For example, Team 1's mean is only slightly above the overall mean, so their residual is small, whereas the Team 2 residual is larger. In general, bigger deviations around the overall mean results in a larger tau 00 or level 2 variance, indicating more between team variability. When deviations from the overall mean are small, the level 2 variance will be small. This concludes our dive in HLM's level 1 and level 2 equations. I want to next touch on a few useful points before doing a quick software demonstration. The first nifty trick I want to show you is plugging in the level 2 equation into the level 1 equation to get a single reduced form representation. All we have to do is replace the level 1 random intercept, circled in yellow, with the right side of the level 2 equation, circled in red. This gives us one equation that basically moves us from HLM or multi-level land to the world of mixed models. Speaking of, you can see why mixed models get their name. They consist of both fixed and random parts. The fixed part is the overall mean, which is constant, whereas the random part has effects that vary across level 1 and level 2 units. When you fit these models to real data with software, the fixed effect will be estimated as a coefficient, gamma 00, whereas the random effects will be variances, tau 00 for U0j, and sigma squared for Rij. The interclass correlation, or ICC, is a useful value for quantifying the level of dependence in your data. The ICC can be interpreted as the proportion of variance in your outcome due to between-group differences, so it's kind of like an R-squared in regression or ANOVA. You can also think about it as the within-cluster correlation among micro level 1 units. For reference, standard linear models requiring independence assume the ICC is 0. Calculating the ICC is easy. It is simply the between-group variance divided by the total variance, or equivalently tau 00 divided by the sum of tau 00 and sigma squared. That wraps up my intro to HLM and the random effects ANOVA model. Now we're going to move on to the HLM software demo. BPG tutorial, BPG tutorial, it's better than sitting in class. In this demo, we're going to fit a random effects ANOVA model to a dataset looking at employee job satisfaction. All the materials needed to replicate these analyses will be available at the website linked below, so check those out if you're interested. Note that these data closely parallel our ongoing example, except now there are going to be 100 teams with 5 employees each, so a total of 500 employees. Okay, we're inside the HLM software program. The first thing we want to do is grab that MDM file. To do so, go up to File, select Create a New Model using an existing MDM file, and then just select this HLM Video 1 file and click Open. You can grab this file from the link in the description below if you want it. Now we're going to concentrate on this level 1 section. All we want to do is identify the job satisfaction variable, left click on that, and in doing so we can select it as the outcome variable. This automatically gives us the random effects ANOVA model. You can see this through the level 1 and level 2 equations. So at level 1 we say job satisfaction equals the random intercept plus that level 1 residual. And the level 2 model says that the random intercept equals the overall job satisfaction mean gamma 00 plus the team specific deviation. If we want to run it, go to Run Analysis, run the model shown, and it'll do its thing and produce some output for us. Okay, we're in the HLM output. The first thing we want to do is make sure the data are correct. So we can see that the maximum number of level 1 units is 500, which makes sense because there are 500 employees. And the maximum number of level 2 units is 100 because there are 100 teams. So everything looks okay there. The other thing we might want to check out is how the model is specified. This gives us the level 1 equation, the level 2 equation, as well as that mixed model representation, which is also known as the reduced form equation. Scrolling down gives us information on that fixed intercept effect. We're going to look in the table under final estimation of fixed effects, and you can see gamma 00 is estimated to be 6.11 with a p-value less than 0.001. This indicates that the overall average job satisfaction score was 6.11, and that is significantly different from 0. Moving on, we can investigate the level 2 and level 1 variance components. That information's in the table underneath final estimation of variance components. The first row gives us details on the between team or level 2 variance. So if we look at that second column, the between team variance is estimated to be 0.61 with a p-value less than 0.001. This indicates that there's significant between team variability in terms of job satisfaction. Turning to the level 1 or residual variance, we get an estimate of 0.99. In other words, there's more within team variability across employees than there is between team variability. Another way to investigate the level of dependency in our data is calculating the intra-class correlation, or ICC. Recall that the ICC is just a level 2 variance divided by the total variance. So in this case, we get 0.61 divided by the sum of 0.61 and 0.99. This means the ICC is 0.38, or about 38% of the variance in job satisfaction scores are due to between team differences. Another way to think about it is, within team, employees are correlated 0.38. Well, you made it to the end. I hope you found this video on the basics of HLM useful. If you did, please like, share, subscribe. We're going to be doing a bunch of different topics relating to HLM and multi-level modeling in the future. Things like growth curves, centering, disaggregating between and within person effects, all kinds of different stuff. So if that's something you might be interested in, you might want to follow us. Also, if you have any questions or thoughts, throw them in the comments. I'll do my best to get back to you. Thanks. Until next time.